Thank you. Yes, nice to meet you. I'm Yokokura. And here I like to give a relation of thermodynamic, entropy, and the dynamics of the gravity. And this work is based on these two papers, and the new one should appear next month. Okay. In the physics, the information is represented by sun or excited quantum state psi. And in the context of semi-classical setup, and any object like this, right? And this object. And the object is in principle a collection of excitations of semi-classical degrees of freedom according to the our state psi. So in my talk, there's some small amount intuitively represents excitation of degrees of freedom. Okay. So of course, the information has excitation energy and as a momentum tensor, right? And this excitation energy, of course, carves space-time are satisfying the semi-classical Einstein equation. So in this sense, the self-gravity of the excitation is represented by in this way. So intuitively, you can say this term corresponds to the weight of information. Okay, this is a key word in my talk. Now, we have our fundamental question. What can we understand the meaning of information in the semi-classical Einstein equation? So in here, I will give just a rough idea. So I'm sorry, I don't have the complete the formulation, but here I will give just a rough idea. Yeah. The answer is entropy should be given by the number of states satisfying the semi-classical Einstein equation for a geometry mu. So suppose we have some geometry mu, right? And as I said, this geometry should be determined by some energy momentum distribution in a consistent way with this dynamics, of course. But the point is here, and if the energy momentum excitation is sufficiently high, and then you can expect there are many possible states that can represent the same macroscopic energy momentum distribution. But microscopically, of course, each state are different, each states are different microscopically, right? So, however, after some coarse-graining procedure, you had coarse-grained energy momentum distribution. That distribution can be represented by many possible states. In that sense, this guys gives you an entropy. So, in this sense, our entropy depends on the self-gravity. And if you like, you can say entropy can be geometrized by the dynamics of the gravity. So I will give one good example, this one. Self-gravitating thermal radiation. So suppose you have a spherical static distribution of on the thermal radiation, and the sizes or radiuses are, but you have to consider self-gravity. So in that means that you solve this equation consistent with this Boltzmann law locally, right? Locally, and then you get this very different behavior, right? So if you neglect self-gravity, and of course the entropy proportional to R to the cube, just a volume law, right? Just use your textbook result. However, including the self-gravity, you have very different behavior. In this sense, entropy depends on the self-gravity. Now, this is a tricky question. What is space-time that maximizes the entropy in a finite region? This one. Static and spherical, and the size is a capital R, and the mass is m. Okay. So to address, this question, here we focus on a highly excited state, and we only consider a class of spherical and static spacetime without trapped surface. Okay, let's focus on such class. To express such space-times, we use this ansatz. This part is for exterior, right, outside. So just a vacuum short-circuit metric. And A0 means this one, just a short-circuit radius for total radiant energy. But our interior part is very non-trivial usually. And they can be represented by two functions, AR and the capital AR. And here, this small AR means the AR gives on the position of the would-be or trapped or surface, right? So, and here, this red one is a key, and this gives a no trapped surface condition. Intuitively, this means our position R must be outside the position of the would-be trapped or surface, at least by our typical wavelength around R, right? Otherwise, you cannot describe this configuration in a semi-classical way, right? Or the excitation of semi-classical degrees of freedom in that sense, right? Please be careful. This is quantum mechanical, right? Not just a classical geometry in some sense, right? Okay. So, and from now on, I like to derive our universal upper bound. And now we have some highly excited state psi. So physically, we can expect that there are many excited quanta like this. Okay, thank you. Yeah, like this. And the energy, typical energy scale is very, very high. So in the typical the wavelength should be short, right? Short. And then if you focus on our small subregion around a point, and then inside of the small subregion, you have many excitations. So, and using such many numbers, you can use statistical argument, right? According to the usual statistical mechanics. And then using such a typical behavior, you can evaluate entropy density, small s. This is entropy density is a density per proper radial length. So the total entropy is defined like this. Okay. Yes. Oh, sorry. Yeah. Yeah. So and yeah, and from here we can use this upper bound or this inequality coming from no trapped surface. We can get this form. And furthermore, to introduce the self-gravity of the excitation, we solve Hamiltonian constraint, and then you get this red one. This is the upper bound. As you can see, and Planck length appear in the denominator, right? So and this upper bound is fixed by the total size R and the energy distribution AR. And I have one comment, this upper bound can reduce to the so-called Bekenstein bound, but this case result contains all the self-gravity. And now we want to see what geometry satisfy this saturation condition. So to get it, we solve this the non-saturating version of the no trapped surface condition, this one, together with some typical relations. And then we apply to the thermodynamic consistency because our state is sufficiently high and highly excited. So in this thermodynamics behavior can be expected. And then here we want to focus on the physical geometry. So let's import no singularity. So then you get uniquely this metric. Okay, so here this metric contains two parameters, sigma and eta. Sigma is constant, but order is n times LP square, and n is just a number, order one number, but it is sufficiently large, and eta is also dimensionless constant. And later, these two parameters will be determined dynamically by solving semi-classical Einstein equation in a self-consistent way. Okay. And here, this capital R represents the size of the this excitation. The position can be determined by some thermodynamic condition. And I have one comment. This metric can be obtained our semi-classical time evolution for the formation process. So, and in that sense, this is physical, I think. Okay, I will explain the meaning of this metric. So, it has this energy momentum tensor. As you can see, and energy density is a positive, and the radial pressure is proportional to the energy density. But our tangential pressure is very, very large. As you can see, this is the order one. So order one means the pressure is near Planckian. So in this sense, this doesn't represent fluid. And the curvature are close to Planckian, like this. So, however, if you have a large n, this order is still smaller than Planck scale. So, and the semi-classical description is valid, right? So, however, why are such large tangential pressure appear physically? I have explained. I have one explanation. The point is, if you have a large curvature in the geometry, and then such a large curvature induces vacuum fluctuation modes with angular momentum, right? Even though such mode doesn't appear in the initial quantum state, right? Dynamically, such a curvature induces the vacuum fluctuation. This vacuum fluctuation produces this tangential pressure. And thanks to this pressure, the configuration is supported. And then you get finite curvature. Okay, finally, here I evaluate the entropy of this system. First, we can check that any degrees of freedom behaves like local thermostat in the radial direction at this local temperature. As you can see, this local temperature is close to Planckian temperature. And we can use thermodynamic relations locally to evaluate entropy density in this way. And then integrated over this entropy density, then you can reproduce area rho exactly. The point is here parameter sigma cancels out in the measure part, GRR measure, and entropy density cancels out, and then you get universal coefficient 1/4. Okay, this is the last slide. So the question is, does the metric satisfy semi-classical Einstein equation self-consistently? Yes. So, but in the first talk by Mark, And this program is generically very difficult, but the special good point is here. The metric is a Walpole product of AdS2 times S2. So thanks to this highly symmetric structure, you can set a program to evaluate, renormalize energy momentum tensor in this way. So and you can you can evaluate right-hand side and solve this equation. Then you get our self-consistent value of sigma and eta. And here, capital N is here I used one example, N3 scalar fields. So in this way, the metric is non-perturbative solution. Okay, conclusion. In this talk, I have considered the weight of information and used typical behavior, and then the solved Einstein equation, semi-cluster Einstein equation non-perturbatively, and then we get this entropy upper bound. And the saturating condition comes from this metric. Okay, so if a black hole is characterized as a quantum medieval system with entropy area rho, and then this configuration can be one candidate. Okay, thank you very much.
Thank you very much. Questions?
Hi, thanks a lot for the talk. Could you back to some previous slides? Because at some point, one more, sorry. You mentioned some kind of, this one, thermodynamical consistency. Can you develop a little bit what you mean by thermodynamical consistency? What kind of...
here, and if here, explicitly, that condition means all the pressure are positive.
Okay, and a quick question, what's the Newtonian limit of this? Newtonian limit. Can you consider a Newtonian limit of this geometry?
Yeah, so this is a non-perturbative solution. So you cannot take H bar 0 limit or G 0 limit. You cannot take it.
Okay, thank you.
Thank you. So I guess you're not saying that this is a black hole mimicker.
Yeah, maybe this is a kind of black hole mimicker because, as you can see, and this A0 is just a short slit radius, and on the other hand, this subleading term is 1 nova A. So this is very small.
Right. Okay, right. But if it is, then if you collide two such things, you would produce gravitational waves, and then you could test it, right?
Yeah, in principle, yes, and I'm very interested in to study such phenomenology.
Okay, thank you.
Thank you.
So maybe I've misunderstood some points, but you talk about entropy density, but of course things in quantum field theory are highly correlated over space-time regions, so you cannot simply add the entropy of two neighboring regions together and say, yeah, this is the total entropy. So what do you mean by this exactly? And secondly, you very easily seem to relate this entropy density to the stress energy tensor. Now, I believe this can be done in some conformal field theories, but on general curved spacetimes, I really don't know how this this ought to work.
Yeah, thank you. So, and your first comment is indeed what I'm now considering, right? So, and as you're saying, entropy is by definition non-local quantity, right? So, and unlike energy momentum tensor, right? So, and so to control such non-locality, we have to be careful, right? So here, my idea is if you consider very, very highly excited state, and then our typical wavelengths should be very short, right? So and then somehow and somehow and you can define entropy density phenomenologically first. And but eventually I want to formulate this one more precisely in a field theoretic way. So, but I'm sorry, at this side, I don't know
So
the idea.
then you would use some kind of relative entropy or something like that.
Yeah, that is one direction. I think so. Thank you. Yes.
And would you say this is related to these generalized second law kind of
Yeah.
considerations?
Yeah.
or-
So, and if this is a black hole, right? And then the generalized second law is just a result of usual second law, I think.
Okay.
Right? Yeah. So and the second to the second question from here to here, and I used on the sun our typical relation. I use such relation. The relation can connect the entropy density and energy distribution, energy density.